Now we start with the second chapter, and this will be some fundamentals of scholastic calculus. So these are the basics of the basics, I could say. Okay, so I'll start with here. Okay, so these are some fundamentals. Okay, and we're going to talk about sets, functions, relations, stuff like that. Okay, because we need some basic definitions regarding this. Okay, so we here, for instance, now of course I think that you know what a superset and a subset is. Okay, so basically this is the first definition that you can also see in the lecture notes. So let's say, for instance, A is a subset of B. Okay, now this is the notation. So here you can see that of course A is a subset. Okay, subset, you see. Okay, and here in that sense, B is called a superset. Okay. Okay. Now, guys, superset. That is actually this is a word that doesn't exist in German. Okay, so the Germans don't say superset. I mean, in German, if you would translate that, we would call Supersatz. Okay, but the Supersatz is a concept of bodybuilding. Okay, so there is another. Actually, this is a training method as well as in English. Okay, so superset has nothing to do with bodybuilding. Okay, so please do not mix it up. Okay. All right, I'm not joking. Okay, so you can Google it if you want to know what superset in bodybuilding means. Just Google it. Okay. Okay, superset. All right, but not bodybuilding. Okay, just for you to know. Okay, so what does it mean actually, formally speaking, if A is a superset of B? Yeah.
As far as I know, A is also a subset of itself.
Yes, that's right.
So the question is A also a superset of itself?
Yes, yes, that's right. Okay, so because, I mean, the formal definition is, I mean, this is just a notation, I'm explaining it here. But the formal definition is if you have something, okay, which is an element of A, okay, and this implies that it's an element of B. Okay, you see? So this is the definition of it. That's a formal definition. Okay, you can see that here. We need propositional calculus to understand it. So, I mean, you can see this here that this is sufficient for that one. You see? I mean, that was what we were doing Wednesday. So this is what you have. All right. Okay. So if something is in A, then it implies that it's in B, of course, and that means, I mean, the implication that you are. I mean, I put this in remark. Okay. That was part of the previous assignment, okay, remarks. So we have that actually A is a subset and a superset of itself, okay, just for any set that exists, okay, and that statement is true because if something is in A, then it's in A, right? Okay, I mean it's obvious. Okay, so any set is a subset and a superset of itself. All right, it's not a strict subset and not a strict superset, okay, because a strict subset would be something that is not equal, okay, so that case is excluded in that sense, but is actually true for any set and as there exists. So this is a statement that is of course true because directly follows here from this definition. All right, so this is the formal definition. Okay, guys, I hope that this is clear. Right? Yeah, you got a question.
How do you define a strict subset then?
A strict set. So here in this case, okay. So the notation. I mean, let me just give you an example for that. So this would be an example. Okay. So example. Right. I apologize. Use different colors. So the strict subset would be. I mean, the notation for that is this. Okay. This is the notation. Okay, so which means that this is equivalent to what? Maybe how you could define this. So here in that case, A is a strict subset of B. How would you define that? Okay, so here, of course, A is a subset of B, and what? Yeah, not equal, right? So here that's the definition. Okay, so this is how you define a strict subset. Okay, so here in this case, if that is true, then of course you would have that. A is a strict subset of B. Okay, so here A is a strict subset of B. Okay. I don't know if the expression strict superset exists, okay? I'm not sure, okay? In bodybuilding, there is a strict superset as well, okay? But anyway, I'm not talking about that. Yeah?
Is a different sign at the equal sign a different?
Yeah, they're not equal, sorry. I missed that. Yeah, they're not equal. So A is not equal to B. I apologize. Okay, that was, I think, what I was saying, but I didn't know. Maybe it's too early or something. I'm not sure. Okay, I'm sorry about it. Anyway, okay, so that's correct. And let's consider the next definition, namely the so-called Cartesian product. Okay, so this will be the next definition. Okay, so I mean, of course, that corresponds, guys. Okay, before we stop with that, let me explain. That corresponds to actually to propositional calculus, namely the implication. Okay, so if A is a subset of B and B is a superset of A, then you can actually say that A implies B and B implies A, and that's how it relates to it. Okay. Of course, you're aware of the following notation. So, for instance, before I define Cartesian product, so this is the union. Okay. So this is the union. This is the intersection. Okay. So this is the set difference. Okay. And A bar, okay, is a complement. Okay? I hope that you are aware of these operators. I didn't mention them in the lecture notes, but I assume that you know them. Now, these operators also correspond to the following. I mean, you can see this here. This is what set theory is, and these operators also correspond to propositional calculus. How does this correspond to the union? I mean, what would be the union operator? So what the union for set theory is actually the disjunction for the propositional calculus. Do you know that? Okay, so this is how it corresponds. The intersection is the conjunction, right? Okay, and the complement is the negation. So this is how it corresponds to it. Okay, and this is actually the difference is the same thing as A and not B. Okay, so here we have, of course, that the difference is equal to A. Actually the intersection of A and the complement of B. This is the difference. That's equal. Okay, so that's how we actually denote this. A and not B, right? In terms of the propositional calculus. Good. Now, what is a Cartesian product? And that's going to be the next definition. Okay. Maybe you can't read this. I can't read it myself, so. Okay. Cartesian product, okay? Namely, the Cartesian product of two sets. The Cartesian product of two sets is as follows. So you say you don't say A times B, all right? You say A by B. This is how it's actually pronounced, and that is the following definition. So I'm defining it right now. That is, of course, a set, okay? So that parentheses denotes always a set. And a set of all elements, let's say, that there is, okay? And of course, we namely have, here in this case, we have a set of pairs, okay? So that's how it actually is denoted here. So this is actually, I mean, so far would be radius follows, so you pronounce. And this is the set of pairs, so X and Y considered to be pairs, okay? With the property, okay? This is actually the condition that you can see that here, that X is from A and Y is from B. Okay, so this is actually a set of pairs that you can construct from these two sets. Okay, let me just give you an example to that. So this is what the Cartesian product is. Okay, so that is the Cartesian product of A and B. And let me just give you an example. You've probably seen this, but you might not be aware of what it is. So let me just give you an example. So here you have a set that consists of the elements 1, 2, and 3. And let's say that B consists of the elements 0 and 1. Okay? And now you would generate the Cartesian product of A and B. Now, this is actually what you need to do. You have to construct a set of all pairs that there exists regarding A and B, but you have to be aware that the first entry is always actually from set A, and the second entry of the pair is from B. So here it means that the set of ordered pairs, that is actually better. So the Cartesian product is a set of ordered pairs. Okay, let me just add this here to this. So this is a set of ordered pairs from A to B. Okay, a set of ordered pairs, okay, from A and B, okay, and then you can see this here from the example. I mean, there are different notations to write pairs, okay, so either you write it like this as a row vector, or you can write them as a column vector, it doesn't matter. So basically what you have here is, I mean, the first entry is actually always from the set A, and the second entry is always from the set B. So here, for instance, 1, 0, okay, would be the first, okay, 1, 1 would be the second, all right, so this is how it goes. So he would have 2, 0, sorry, that's a different one. Here you would have 2 and 1, using different colors, so you actually understand where these elements are coming from. And the last one will be 3, 0, okay, and 3 and 1, okay? You understand? If I'm not mistaken, right? Oh, okay. So these are the elements from okay, from set A, the first ones, and the second entries are from B. Okay. As you can see, if you change the order, so if you would generate, let's say, the Cartesian product of B by A, all right, then you would get something else. Okay, because here in that case, the first entry is actually from A and from B, sorry, and the second entry is from A. Okay, so A by B is not the same thing as B by A in general. Okay, so here in that case, the operator for the Cartesian product is not commutative in general. All right, so this is actually something that you're supposed to understand. So here, for instance, I mean, you will also get 6 pairs. All right, so I'm just preparing them. Okay, so you would get 6 pairs, but you would get actually different ones, because the first entry has to be from the set B. Okay, so here you would have 0, let's say, all right, and here you would have 1. I'm following the same analogy here. So in that case, you would have 1, 1. No, 1, 2, and 3. Sorry, and here as well, 1, 2, and 3. So as you can see here, okay, so this is what we conclude. So A by B is not the same thing as B by A, and that is also true in general. All right, so that operator is not commutative, as we'll see. Okay, so this is what the Cartesian product is. I mean, I hope that you've seen this somewhere, you know, when you talk about vector spaces or whatever. All right, okay. Now what I'm going to do is I'm going to define a subset on a Cartesian product, and a subset of the Cartesian product is called a relation. Okay, so that's going to be the next definition, guys. Okay, so let's say I'm going to generate a subset here. I mean, taking like, for instance, any of them. Okay, so let's keep that one as an example. So let's say R will be a subset of A, and this is going to be like whatever. I'm just randomly selecting some pairs. Okay, so we define this. Okay, so this is just an arbitrary definition. Okay, so we define R, and that should be like, for instance, like this. So this is 1 and 0. Okay, so this is the first one, and 1, 1. Okay. Now you can see clearly, okay, that R, okay, is a subset of the Cartesian product A by B. Okay, and any subset of the Cartesian product A by B. I hope you see this, right? Okay, because the elements that you have here in R, okay, so these are the ones, okay, that these are elements also from the Cartesian product A by B. Okay, so the set R is actually a subset of A by B. You understand this? So any subset of a Cartesian product is referred to as a relation. Okay, so this is a relation, and let me just okay, so R. So hence, okay, let me just give you that, and then this is a definition. So hence, R is a relation. All right, so that's going to be the new definition, namely the relation on the Cartesian product A by B. Okay. All right, and that's going to be the next definition. All right, so here you can. This is what you also find in your lecture notes. Okay, so definition. Okay, so any subset of a Cartesian product. All right. Let me just repeat this here. So I have to capital C. Okay, so Cartesian product is called a relation. Okay? And if you're talking about the Cartesian product of a set by itself, okay, so let's say, if let's say R, okay, which is a subset of, let's say, a Cartesian product of a set by itself, okay, then R is called a relation, okay, on the set A. Okay, so this is what we have here. Okay, so you can also define A by A, which is A squared. You can use that notation as well. And if you have something like that, then you can say that R is, capital R is a relation on a set A. Yes?
What does it say in front of the R?
It is actually that this is a subset, okay?
Oh, okay.
So that's what it is, okay? So if you define a Cartesian product where you take a set and you construct a Cartesian product of a set by itself, okay, so A by A, for instance, then you can say that, and if you have a subset on that, then R would be a relation on it. Okay, maybe I'm going to give you an example to that so you understand it better, because that it's not difficult to understand, but it might be confusing. Okay, so let me just give you an example to that. So this will be a little example. So let's say that A would be the set that consists of the numbers 0 and 1, okay? And we define the Cartesian product A by A, which is what? Okay, you can also write that as follows, so A squared, okay? I don't know if you've seen the notation, maybe R squared or something like that for vector spaces or anything like that. So here in this case, okay, so we'd have the set of ordered pairs, so you have 0, 0, okay? You would have 0, 1, you would have 1, 0, and then you would have 1, 1 as the element, okay? So this is the Cartesian product. And let's say you have a subset on that. So here, for instance, R would be like whatever, where the entries are equal, okay? So 0, 0, and 1, 1, okay? Now here you would say that R is a subset of the Cartesian product A by A, which means that you can say that R is a relation on the set A. You understand this?
Yeah.
That is a concept, okay? I think that demonstrates what it is. Okay, so that basically you can say that you have your relation on that set, okay? Which is defined as a subset of the Cartesian product. Now, of course, in the general case, you can generate a Cartesian product, let's say A by A, so you can add this, multiple times whatsoever. But you have to have that at least twice as a Cartesian product, a set of ordered pairs or set of ordered triples or stuff like that. Okay, so this is what relations are about. Okay, now we distinguish. I'm going to give you actually an example, which is more like a real life example, but I hope you understand this concept because we distinguish between, basic properties a relation can have. For instance, the most important ones are reflexivity, transitivity, and symmetry. Okay, so this is what you see actually next in lecture notes, but I hope that this example demonstrates what the relation is. Okay, can I continue, guys? Okay, all right, so next we define actually what reflexivity means. So a relation, let's say, suppose that we have, for instance, and this is going to be the next definition, guys. Okay. So, before I continue, okay, so suppose that we have a relation. I didn't tell you about that notation here. So, suppose that you have a relation, let's say R is a subset of a Cartesian product of, let's say, the set omega, so omega by omega. And you can denote this also as follows. So, if you have something like that, then this would be the same thing as saying that, you can say that you have, let's say, for instance, okay, so it's something if X is an element, or X and Y, okay, sorry, this is the pet, is is an element of the relation where actually x and y are elements of omega. Okay, so we have a relation on the set omega, of course. Then this might be denoted as simply as just say x relates to y, okay, where actually x and y are from omega. Okay, so this is the same thing. Okay. Okay, because I use this notation more frequently than the other. Okay, that's a simple one. So that is actually the same thing. So here, suppose that you have a relation which is defined on the set omega. So then you can say if something is an element of the relation, then let's say x and y are as an ordered pair as an element of the relation, then you can actually note this by the following. So you can use a tilde notation. So x relates to y. This is how it's pronounced. Okay. So you can say that x relates to y. Let me add this here. Okay, so I put this in quotation marks. X relates to y. Okay, so this is how it's pronounced. Okay, so if x relates to y, then the set of ordered pairs from x and y is an element of the relation. That's it. And the relation is, of course, a subset of a Cartesian product of the set omega by itself, because omega is the set where actually x and y are coming from. All right? Do you understand this? Okay, so for instance, the previous example, 1 relates to 0 and 0 relates to 1, as we had that in the previous example. Okay, guys. Now, let me just continue, because that's actually what we're talking about. We're talking about so-called equivalence relations. And equivalence relations will be relations that are reflexive, symmetric, and transitive. Okay? So, let me just give you the definition. So, okay, a relation, and I use this notation, so the tilde, okay, so relation tilde on the set omega is called reflexive. Okay, so that's the first one. If any x that is an element of omega relates to itself. Okay? So any x relates to itself as well. Okay? Where actually x is an element of omega, obviously. Okay? So if any element relates to itself, then the relation is called reflexive, and that must be true for all elements. Okay, later you're going to see an example, but we had in the previous example that was the previous example that 0 relates to 0 and 1 relates to 1, so that relation here, that example was reflexive. All right? Yeah.
So in this example, which we had before, we have to take all 0, 0, 1, 1,
yes.
and so on.
And if you have more elements, then you have 2 must also relate to 2.
Yeah.
So each element must relate to itself, no matter what.
You're not allowed to take the other ones.
Which ones? Any of them. You have to take any of them. So that must be true for all elements. So all elements on a relation must relate to itself. Okay, I'm going to give you an example so you understand that.
But it theoretically could relate to itself and to some others.
Yeah, but okay, so if it relates to itself, it doesn't mean that it doesn't relate to anything else. Okay? But it has to relate to itself.
At least.
At least, exactly. All right. Okay? You get that? Later we consider an example so you understand what it is. Okay, so then the relation is called symmetry. Okay? If we have that, if x relates to y, then this is equivalent to that y also relates to x. Okay, so if x relates to y, that this must imply that y relates to x, and of course vice versa, because if y relates to x, then this must imply that x will also relate to y. Okay, and I just add here that x and y are just arbitrary elements from the set omega. Okay, so that is a symmetric relation. So basically, you see this here. If x relates to y, that must be equivalent to y relates to x. So if x, you can say, basically we learned this. X relates to y if and only if y relates to x. You understand that? Equivalency. Good. And the third property is that the relation is transitive. Okay? Transitive if, let's say we have that, for instance, if x relates to y, so this is given, and y relates to z, okay, then this must imply that x must relate to z. Okay? And of course, here we have that x, y, and z are just arbitrary elements of omega. So if that statement is true, namely that if x relates to y and y relates to z, then x must also relate to z. Okay, now let me give you an example. So in that case, if a relation is transitive, reflexive, and symmetric, then we have a so-called equivalence relation. Okay, so equivalence relation is a relation that is reflexive, symmetric, and transitive. Okay? Maybe you've seen this somewhere in, like, for instance, I think microeconomics and stuff like that. You know, where they have a set of goods and whatsoever, and they have this, the kind of rational behavior or whatsoever. So if x, the good x, is better than y, and y is better than z, then x must be better than z as well. Okay, let's say, for instance, for soccer, that is not true. Okay, so if, let's say, the team X beats Y and team Y beats team Z, then does it imply that team X beats team Z as well? Okay, I mean, in most cases that is, but it can happen that team Z beats team X. Okay, as we've seen this, for instance, in the soccer championship, world championship 3 years ago. 3 years ago. We have it this year. This year, right? This year?
Yeah, this year.
4 years ago. Ah, damn. Anyway, okay. So, okay, let me just give you an example where you consider, like, some kind of relation. So, for instance, let's say that x and y are people. Okay. So x and y are actually elements of omega, and omega is the set of all people. All right. And let's say we define a relation on that set, namely as follows. So we define x relates to y if and only if x hates y. Okay? All right? You understand that? Okay? So this is the relation that I define. And now let's see if this relation is reflexive, either reflexive, transitive, or symmetric, or none of them. Okay, so let's say we examine reflexivity. Now, in order for this relation to be reflexive, we have to make sure that each element relates to itself. What would that mean? So any person hates itself, him or herself or herself. Now, I don't know if that is true or not. Maybe there is a kind of tendency for everyone, If you like kind of smoking, right? You hate yourself because there's some kind of psychological issues, right? But I'm not talking about that, or excessive drinking or something like that. So there is, a kind of self-hatred that you can interpret that as a pathological issue, but I'm not talking about this. So x relates to y is not the case in general. Okay, so it's not the case in general.
Wait, it's x relates to y or x relates to
x relates to x, sorry. Okay, so this is right. Yeah, so if you, for instance, you're a kind of narcissistic person or whatever, so then you kind of love yourself, you kind of looking in the mirror and stuff, and you do this all the time, so then you would probably, maybe this is also kind of self-hatred, whatever, I'm not sure, but you cannot say that from, let's say, from the pathological point of view that you hate yourself. Okay, so that is not true. So hence, in that case, the relation is not reflexive. You understand? Okay, you understand. So now, what about symmetry, guys? Okay, so let's examine that. What does it mean? So suppose that x hates y, okay? Does that imply that y hates x? No, right? So that does not imply in general that y hates x. Why is that? I mean, for instance, you have, you know, whatever, kind of stalker or something, right? You hate your stalker, but your stalker probably doesn't hate you, so understand that. So, I mean, I'm not saying that this is true in all cases, maybe, but in most cases it is. So, I mean, but at least, you know, you cannot imply that, you know, just because you hate someone, it doesn't mean that, you know, that he or she hates you. Okay, so hence relation is not symmetric. I mean, in most cases that is. So if you find someone hating, I mean, you find yourself hating someone, that the likelihood that this person hates you is relatively high. Okay, but it has to be true in all cases. So I'm not talking about, you know, certain examples, whatever. Right.
This tilde symbol, you just use this in this case
as a relation.
As some relation.
Yeah, this is the relation. No, that is the relation that we're talking about. So this is the
what do you find above?
Yeah, what I defined here. Okay, so that is the definition. Okay, so here, I mean, that was the example that I gave. So this is the definition of the relation here. So this is the definition of, let's say, of the relation here.
And just from my understanding, for example, in micro 2, we find this as is equally good or something. This symbol.
What do you mean? No, it means that this is just a relation. I mean,
some relation.
Yeah. I mean, here in this example, you know, you have a specific one. But here, this is like, you know, this is the relation. I mean, this is the notation for that. Okay, so you could denote this. I mean, this is relatively easy to define a relation. I mean, to express a relation like that. Okay, so here, for instance, you find it here because that is actually more practical in that sense than to denote it like that. Okay. All right. Because I don't need, you know, to actually define specifically what, you know, how the set looks like. Okay. X hates Y. Okay, how would you define this in terms of, you know, when you have a set of people, you know, so that would be not, you know, that would be quite challenging, you know, to express that in formal terms. So that's more practical in that sense. Okay. Okay. So this is how it looks like. And what about transitivity, guys? Okay. Okay, so I'm using like this, so maybe I use the notation. So suppose that X hates Y, all right, and Y hates Z. Okay. Does that mean that X hates Z? No. Okay, so that is not actually not the case in general. So hence the relation is not transitive either. Okay, and of course, this relation is not an equivalence relation. That is obvious. Okay. All right. Okay, let me just give you another one. Okay, so I mean, this is like, you know, from practical reasons, might be interesting, you know, real life examples. All right, but let's consider, for instance, a relation which is defined in a set of real numbers. So I'm defining X relates to Y if and only if X is less than or equal to Y. Okay? And I'm defining this on a set of real numbers. Okay? Okay, so here you have a relation on the set of real numbers. Okay, so this is the relation. Now, I would like to examine if that relation is reflexive, symmetric, or transitive, or whatsoever. Is this relation reflexive? Okay, so first, reflexivity. Okay? Does, let's say, if you have like an X, for instance, okay? So does it relate to itself? That is true because here in that case, I mean, you can see this, that X is less than or equal to X. Okay, so that is a true statement. Okay, so hence and therefore, the relation is reflexive. Okay, that is obvious.
Is it in that case less or equal or less and equal?
Less than or
equal is
less than or.
sensitive.
It doesn't matter. That statement is always true.
Okay.
0 is not greater than 0. 1 is not greater than 1. That is always true. Okay? As we talked before, I mean, you remember this. Okay, so, I mean, let me repeat that here because we had it last time. So x is less than or equal to y if and only if x is less than y or x is equal to y.
Yeah. Okay.
Alright? And this is logical disjunction, which means that logical disjunction is true if and only if at least one of the statements is true. Now, if x and x are equal, or x and y are equal, then of course you can say that x is not greater than y. You alright? Okay? Does it make sense? Okay, so that is confusing, but you know, I have to make sure that you understand this. So, second, what about the symmetry, guys? Okay, so what about the symmetry? Let's say if x relates to y, okay, does it mean that y relates to x as well? Is that the case? No, not necessarily. For instance, I mean, you can just use one example. So you can say that, here for instance, all right, so, I mean, let's say, I mean, just give you an example. So 0 is less than or equal to 1, okay? But on the other hand, okay, but that is not true on the other way around, okay? So that is not true here, okay? Obviously. So hence, I mean, just if you had just one example, then you can say that the relation is not symmetric. All right? So it's reflexive but not symmetric. And what about transitivity, guys? Okay? What about transitivity? All right?
So if x and y equal 0 at the same time.
But, you know, in that case, if they are equal, then it's symmetric. But, you know, if you just find one example where the symmetry is violated, then the relation is no longer symmetric. So you have this is what I'm trying to say to you. So you need just one example to crash everything in terms of, you know, the property. Okay? So if you find one example for which is not true, then the relation is not symmetric at all. Okay? At all. And what about transitivity, guys? So let's say if x is less than or equal to y and y is less than or equal to some z or something, does that imply that x is less than or equal to z? Okay, that is true. Okay, so here let me just denote this. So if x is less than or equal to y and y is less than or equal to z, then this implies that x is less than or equal to z, which means that the relation is transitive. Okay, so the relation is transitive. All right. So it's reflexive, transitive, but not symmetric. Okay. In that case, so what does it mean? It's not an equivalence relation. Okay. So here we find that this relation is not an equivalence relation. Okay. Now let me just give you an example for an equivalence relation. And you find this example also in your collection of examples that I gave you, and this will be example number 2. All right. Okay, so I would like you to demonstrate that, where you have an example from equivalence relation, which is the relation which is reflexive, transitive, and symmetric. Okay. Can I continue, guys? Okay. You copy this? Okay. You have that, and let me just add that. Okay. So this is example number 2. So here you will have, let's say, a relation which is defined as follows. So x relates to y if and only if the sum of x and y is even. Okay, you know what an even number is. And this relation is defined on the set of natural numbers, but you can say that you can define this also in the set of integers as well. So I'm just taking the set of natural numbers anyway. Okay. And suppose that 0 is included there. I mean, you can include that as well because 0 is an even number. Okay? Okay, guys. Now, what about, first off, what about reflexivity? Okay. Let's say if you have, I mean, does actually, I mean, if you take a natural number, any natural number, no matter what it is, and you add it to itself. Okay, so since we have, I mean, you can say this here, so x plus x is equal to 2x, and 2x is always even, okay? And since, okay, you can see this here, so 2 times x is even for all natural numbers, then we have that relation is reflexive. See? Okay? All right, I'm just making notes here. I mean, you find it in that. Okay, so let's continue with the symmetry, guys. Okay, now is this relation symmetric? Yes or no? And so suppose that x plus y is even. Okay, suppose that this is the case. Then what? Is y plus x also even?
Yes.
Obviously, because the addition is commutative, right? Okay, then y plus x is also even because addition, okay, so this operator is commutative. You know what commutative is, right? Okay, we talked about that. I mean, you know, in terms of the propositional calculus, but if you perform that operator on a set of natural numbers, then you find it also is commutative. So x plus y is equal to y plus x. Okay, so then hence the relation is symmetric. Okay, and what about transitivity, guys? Okay. Okay, what about that? So suppose that we have that x plus y is even and y plus z is even. Okay, so here in that case, you will have that if x plus y is even, then both either are even or odd. All right. So suppose that they're both even. So if x plus y is even and y plus z is even, then you would have that also that z is even. So if x and z are even, then the sum of x and z is even as well. Okay? And if both are odd, namely that if x and y are odd, then and the sum of y plus z is also even, then z must be odd as well. So if then in that case x and z are odd, and hence this implies that the sum of x and z is also even. All right? That's, you know, I mean, to put it simple, but I'm not going to write it down because it takes too much time. Okay, so then this implies that x plus z is even. Okay, so hence the relation is transitive. Okay, so by summarizing the result, the relation is an equivalence relation.
What can we do with that?
I tell you, okay, that has lots and lots of important implications, okay? Especially when you're looking at, for instance, measure theory, okay? So, but you have to know what it is. And even in statistics, guys, there is one basic property that actually the equivalence relation generates a so-called partition of the set in which the equivalence relation is defined. And I'm going to give you what that is, but first off, I need to make sure that you know what equivalence class is, okay? So, and let me just give you an example. So here, this relation was an equivalence relation. You've seen this, okay? So x relates to y if and only if x plus y is even, and this is an equivalence relation. On the set of natural numbers, okay? This is what we have seen, okay? And suppose that this is given. Now I'm going to give you an equivalence class. You know, what is the equivalence class of a certain element, okay? So for instance, let me just to demonstrate that, you know, so the equivalence class, for instance, of X, okay, equivalence class of certain elements, this element X, okay, and I denote this as, I mean, this is not official, but I call this EC, okay, for equivalence class, and equivalence class of X, okay, so that would be the notation, okay, but this is not official, okay, so don't take it literally, but I have to call it somehow, okay, so that will be a set, okay, maybe I'm not using capital letters, okay, so because that's might be confusing, so I just use EC, okay, but you can use capital letters if you just started with that, okay. Now EC is the equivalence class of an element, and what it is. Now guys, this is the set of all, I call it, let's say, I call them Y, okay, the set of all Y's, okay, or a set of all elements on which the relation is defined, where actually you have that X relates to Y. Okay, so what you do is you construct a collection of all elements that relate to the element of X, and then you put them together, and that would be an equivalence class. See what I'm saying? Okay? All right? You understand this? Okay, now let me just, for instance, give you an equivalence class of 2. Okay, so what would be the equivalence class of the number 2? What would be that? So we have to put everything together that relates to the number 2 here in that case. Now, how is this relation defined? Okay, so anything that you add to 2 must be even. Okay, so what about 0? Is 0 in the equivalence class? Right? Okay, because 0 plus 2 equals 2, and 2 is even. Right? Okay, so 0 is in there. What about the number 1? Yes?
Well, I'm wondering, why does it say EX?
Sorry, EC.
Okay.
I don't know. Because I was stupid here at that point. Okay. And sometimes it happens, you know, my brain just switched off, and then I kind of, maybe I was confusing that. Anyway, so I apologize. Okay, so we're talking about the equivalence class of the number 2. Okay, so which numbers are in there? What about, okay, 0 is in there. That's obvious because 0 plus 2 is equal to 2, and 2 is even. What about the number 1? 1 plus 2 equals 3, and 3 is not even, so 1 is not there. What about the number 2? 2 must be in there because that's, you know, we have actually seen that the relation is reflexive, so the number must be there as well. What about 3? 3 is not there. What about 4? 4 is in there, right? 5, not 6 is in there, stuff like that. So all even numbers are in the equivalence class of 2. See what I'm saying? Okay? Right? Okay? What would be, for instance, the equivalence class of the number 1? Okay, so what would be, you know, the equivalence class of that? Okay? What is it? Okay, so which are the numbers that relate to 1? Now, of course, the number 1 itself, because it's reflexive, right? 0 is not there, because 0 plus 1 is not even. Okay? What about 2? 2 plus 1 is not even either, so 2 is not in there. What about 3? Okay, so 3 is in there. What about 5? Okay, 5 is in there. 5 plus 1 is even. What about 4? 4 plus 1 is not even. Okay, so it's not there. You understand? So this is the equivalence class of the element 1. Okay? Now, what about actually these? I mean, these are actually the only 2 equivalence classes that exist. Okay? You see? These are the only 2. Right? You see this? And these are, I mean, you can see that the equivalence classes, okay, generate a partition on this set. I mean, just, I'm going to give you the exact definition of what a partition is. So the equivalence classes generate a partition of the set on which the equivalence relation is defined. Okay, so this is the first property that you can see this here. I mean, I'm going to give you exact definition what a partition is. But you can actually, I mean, we had this action in statistics. I mean, you told me that I thought you, so you're supposed to know this, goddammit. Okay, so a partition is actually a collection of sets that are pairwise and disjoint. Okay, so that's the first property. And if you unify them, then you get actually the set in which the partition is defined. Okay, so the union of the two equals the set of natural numbers, and the two are disjoint. You see? And these are the only two equivalence classes that exist. Okay? And what you also have is, this is what I'm going to show you, is that two equivalence classes are either equal or disjoint. Okay? That is actually what you can see this here. Because what would be actually the equivalence class of the number 4? Let me just add this here. I mean, you don't have to write it down. Wait, what would be the equivalence class of the number 4? What would be that? Yes?
Equivalence class of number 2.
Yes, because you know that contains also the same elements. You see? Okay? So these two equivalence classes would be equal. So here you have that either two equivalence classes are either equal or disjoint. That is the second property that you can see this here. And this statement is actually proved in the example number 3. So I'm going to prove that here as well. Okay, so two equivalence classes are either equal or disjoint. Okay? That was part of the last examination, so I would like you to demonstrate how the proof works. Okay? But you don't have to prove that. All you have to do is actually to give that statement as an answer. So that was, you know, and you had 10 minutes for that, so I think 6 minutes, okay? So that was, I think, more than fair enough. Okay? But at least my estimation anyway. Okay? So and let me just give you that statement. Okay, so that was a question related to equivalence classes, and that was the solution to that. Okay, now first up, I mean, I didn't define what equivalence class is, so let me just do that because I didn't do that here. Okay, so suppose that okay, so suppose that this tilde is an equivalence relation.